Okay. Yeah. Okay. Welcome everyone to this colloquium. A little bit out of the schedule because we have a Thursday, but it's more like an internal presentation given by Philip about VA and all the interface that it has and all the bugs maybe it still has, and also the perspective for future development. Also leading to the implementation week in November, September.
Yeah, in 2 weeks.
Genau, in 2 weeks from now. Okay, so yeah, go ahead, Philip.
Yeah, thanks for this introduction. Hello and welcome everybody. Yeah, virtual acoustics is our auralization framework, which most of you might know. So it's a very large and complex framework with a lot of modules. And when I took over the development like a year or 2 years ago, what I kind of quickly learned was that for many users, the picture of VA is kind of blurry. So it's hard to comprehend the overall concept with what material was there and with what they were working on. So that was the motivation behind this talk. Today I want to recap the general concept behind virtual acoustics. And the occasion also is that there's a new version, and this comes with new features that also make VA more user-friendly. And finally, I would also like to give a few examples of use cases. So how can we apply virtual acoustics to virtual reality scenarios to actually show what VA is actually capable of, because many users just scratch on the surface, so to say. So talking about new features, what were the recent developments? So the developments during the last year. Everything started with the rework of the build environment, which was initiated by Pascal Palenda. This is of course more interesting for developers, but it actually makes working with VA as a developer, building it on your system, much easier. So it's a very nice new feature. And yeah, after that, I started reworking the rendering concept, which allows us to apply VA to new setups, to new scenarios. And finally, and this might be the most important update for users, is that the website of VA was reworked, and this includes a major revision of the documentation. And okay, today, as promised, I will talk about the general concept behind VA. This will be the main part. Then I will introduce this new rendering concept, followed by giving you a quick glimpse on the VA website. And then, if there are any developers out there today, I want to have a quick overview on the new build environment. So this will be very brief, no worries. And finally, we will talk about a few use cases. So let's take a look at the general concept. So VA works with a server-client concept. That means we have on the one side the VA server, which is the actual application that is running, that is doing the audio processing. On the other side, we have the bindings, which a user can talk or use to talk with the VA server over a network protocol. And this means that the server and the interface the user is talking to don't have to be on the same computer. They can be on different computers in the same network. So the difference here now is that while the VA server can only be configured before startup using an ini file, while the interface is used during runtime, so the user can permanently change things in the server through this binding. And there are multiple types of interfaces. So since VA is implemented in C++, the natural interface is also in C++, of course, but there is a wrapper for C# also. And the most commonly used interfaces are script-based interfaces. So there's one for Python and for MATLAB. And MATLAB is actually the most developed interface and the one that is used in, I would say, in most cases. And then when we go to like the full virtual reality, we are working with gaming engines. And there are interfaces for Unity and for Unreal. And the interface for Unreal is hosted by the VR group, by Professor Kohlen, and we are collaborating with them and developing this together. Okay, so that's the general concept of how the communication between the user and the server works, but what is actually happening in the server? What is actually, how is the auralization process actually looking? There are three main components here. So auralization, or the rendering of an auralization, is always based on a scene. And so a scene might be like an actual, or is always based on an actual scenario, like a real world scenario, like here, this aircraft flyover, and deriving from that, or based on that, we derive some objects that we use to create the audio in the end. The second step is the actual rendering process. So based on the scene, based on the objects within the scene, and physics-based models, an audio signal is generated. And finally, there's the reproduction, which is often neglected. So depending on the setup that we have, or where we want to use VA, maybe we want to reproduce the sound via headphones, or we want to use a loudspeaker array, and then we need different reproduction setups. So that's the last key in this chain. And then the final audio is then sent to the sound card. And as we can see here, the user is mainly talking to the scene. So the user can, during runtime, control the scene or the objects within the scene, while the rendering and the reproduction and the settings for the sound cards, they are initialized before startup. So there are only limited options changing the rendering modules and the reproduction modules. So I already talked about this word, modules. Actually, there's not only a single type of rendering in VA, there are multiple types. So we have different modules, and each of those modules, they use different kind of physics in the background, so they have different assumptions about how we render the scene. And also for reproduction, we need different modules depending whether we want to use headphones or loudspeakers, for example. And it's also possible to link one rendering module to multiple reproduction grids. So I can reproduce sound at the same time via headphones and loudspeakers, for example. Okay, now let's take a more detailed look at each of those three steps, starting with the scene. So same example, aircraft flyover. I talked about that we use objects as a starting point for the auralization, and the most important objects are, of course, sound sources, in this case the aircraft, and receivers, which is in this case the listener on this bench. But there's more to it. We need additional meta information for those objects. For example, the source has a driving signal, which we call signal source, and this is typically an anechoic signal which might be recorded or which might be simulated. And then there's directivity describing how the sound is distributed in different directions. And on the receiver side, we might have something similar, namely an HRTF dataset for the directivity at the receiver, which we need for the spatialization of sound. And finally, what's also relevant is the medium in between. So we also want to model the sound propagation, as we see later on. So we need information about the medium, like temperature, speed of sound, and so on. And depending on what kind of rendering we want to do, there might be additional information like obstacles. For example, in this case, you might want to model the floor as well and include this ground reflection. So we need some kind of description for the ground. So yeah, this very complex looking scene might in the end just look like this, so much more simplified, but for the acoustics this might be very sufficient depending on the scenario that we want to realize. Okay, let's move on with the rendering. So yeah, as I said, the rendering is always based on such a scene and on physics-based models. And we always start with this before mentioned source signal, or signal source. So this raw signal that the sound source emits. And within the rendering process, you want to consider the sound propagation. So how is the sound altered while propagating from the source to the receiver? And at the receiver, we want to do some kind of spatialization to get 3D audio in the end. We don't want to have a mono sound or some stereo sound. We want to have actual 3D audio. And for VA, there are 3 types of spatialization. We can use binaural signals, ambisonics encoded signals, or bebop. So those are the 3 options for us. And now there are 2 types of rendering approaches. The first one is FIR-based rendering. In this case, both steps, the sound propagation and the spatialization, are combined in a single impulse response, which we convolve the input signal with. And a typical example for this is our room acoustic scenarios, where we can use binaural room impulse responses, for example, yeah, which we convolve our input signal with. However, the drawback here is that sound propagation and spatialization are considered together in one filter. Another approach is using sound path-based rendering. And in this case, the sound propagation is actually split into 2 steps. First, we simulate geometric sound paths, so the actual rays that connect a source with the receiver. And then we derive acoustic parameters from those sound paths. And I like to call those auralization parameters because those drive the digital signal processing elements. To give you a very simple example, so we could calculate the spreading loss from a sound path, and then this will drive the signal gain at the end. So and this is done for every sound path, and then in the end we accumulate the overall results by adding up for sound paths. And we see the spatialization is an individual step here, which is nice. And it's particularly interesting to use such an approach if we have scenarios where the number of sound paths is limited, like outdoor scenarios. For example, here we only have two sound paths that we are considering, and here there might be a few more. Okay, so those are the 2 concepts for rendering. We will get back to this later, but finally I want to move on with the reproduction modules. So now consider that we have a renderer that gives us a binaural output signal, and we want to reproduce this via headphones. Then a module that we could use is the talk-through, which simply just routes the output signals of the renderer to the channels of the headphones. So it's not really doing much. So why do we actually need a reproduction module here? There might be more sophisticated things we want to do. For example, in this case, we might want to compensate the influence of the headphones by using a compensation filter. And then we can use the headphones reproduction module. Another example, if you want to use loudspeaker-based reproduction, we might have an ambisonic signal now, and then we can use the HOA, so higher order ambisonics module. And for example, in this case, you might have a V-format ambisonic signal as input, and this can be rendered to end channel signal referring to our loudspeaker system. So that's a quick overview why we need reproduction modules. Later in the use cases, there will be additional examples. Okay, so that's about the general concept of VA. Now I want to talk a little bit more about the rendering system, and especially the new rendering system. For this, I go back to the sound path-based rendering, and I want to take a more detailed look on the spatialization. So how do we actually do spatialization in VA? We have a mono input signal that already considers the sound propagation, and then based on the incoming direction at the receiver and the receiver orientation, we can apply a spatialization and end up in an n-channel 3D signal. And there are different approaches, as I said, so binaural filtering, ambisonics encoding, or bebop. And the general approach for all three kinds of spatialization is the same. So, going back to this figure, it seems natural that we can split or handle the sound propagation and spatialization separately. However, what was the case before is that we had specialized rendering systems that were always fixed to one kind of spatialization, which was typical binaural. And those were kind of connected and they were not separated properly. To give you an example, the most commonly used renderer is the binaural free field renderer, so binaural filtering and free fields conditions. And at some point it was extended, so there's an ambisonics free field renderer, as a reverb free field renderer. So three types of rendering system, almost doing the same except for the spatialization. And this means code-wise, there's 3 times the same code within the system, and this is highly, for developer, this is not nice because it really increases the maintenance and is very error prone. On the other hand, there are other renderers like the binaural air traffic noise renderer, where the ambisonics spatialization and reverb spatialization was missing. So how can we change that? It's quite simple. So now there's a new concept. We have, or the new renderers, they are not bound to one type of spatialization anymore. So now there's a free field renderer and an air traffic noise renderer. And we have 3 types of spatialization, which are fully separated. And in our ini file, the VA core ini file, we can now configure those renderers to have a specific spatialization. For example, I can have a binaural free field renderer and an ambisonics air traffic noise renderer. So I'm fully flexible here. I could also create 2 renderers running in parallel, doing 2 kinds of spatializations. And also the nice thing is that this rendering concept is very easy to extend, so it's much more easy to write a new renderer with a new physics behind it than before. Okay, so that was it about the rendering concept. Now I want to give you a quick look on the VA website. So it looks a little bit different, but the general style is the same. And I just want to point out a few things, especially regarding the pages of VA. So let's click on VA. So this is still the same overview as before, but if I now click on documentation, I see here there's a table of contents, which is new, this was not there. So it's much easier to browse through the documentation now. There are much more links within the documentation, so if you are looking for something, it's much easier to find. There's even a search function here, so and yeah, we worked a lot of the text, so it should be much easier to understand and find the things that you're looking for. Also, there's an overview of the rendering and reproduction classes here. So yeah, I would say this is much more user-friendly than before, and I hope that this helps you in the future to configure VA to your need. Okay, let's go back. And now one slide for all the developers out there. I don't know how many there are, but to all others, don't fall asleep. So yeah, as I said, there was a major review of the built environment. And I want to just give you a few ideas why the old environment was not so nice and was really hard to work with. So we are working with a lot of external libraries within VA, so we can't implement everything on our own. And in the old system, we had to do everything manually. That means you had to download the libraries, you had to build them yourself, you had to link them yourself. And that was quite strenuous, and actually what we finally did was there was a pre-compiled list of all libraries on the server, and we would just link to them, which in the end bound us to a very old compiler, because those were linked in a very old, built-in very old compiler from 2013, which is really limiting, especially if you look in the future. And and another drawback was that regarding our Python binding, we had to put this in a separate build because this did not work with the 2013 compiler. So that's, maybe you're aware that there was always this VA full build and this VA bindings build. That's the reason why this was like this. And in the new environment, external libraries are handled automatically. So they download it for you, they are built for you, they are linked for you. And this is all automatic and allows us now to use any modern compiler. And of course, then this also allows us to include VA Python. So while whoever is aware, so this is all CMake based. While this running CMake now takes a little bit longer because it has to download all this data, it is much more automatic and much more user friendly. Okay, so that was it regarding the built environment. So final chapter is the other use cases, so everyone can get online again, all the users. So I want to give you a few examples of how you could configure VA and to work with certain scenarios, starting with a simple setup which is often used for listening experiments, where we have a free fields assumption and use binaural rendering. So that was often used in listening experiments, meaning we have a source and a receiver and consider the medium just regarding speed of sound and propagation delay whatsoever. And we have a source with a directivity and a signal, and the receiver with an HRTF. So a very simple scenario, a very simple scene. And this was often used with the headphones reproduction module, so for compensating the headphones transfer function, or sometimes also using a CTC. So this is a module that I didn't mention before. For example, in our Hearing booth, you can run a CTC and play the binaural signals over over loudspeakers. Another example is ambient sound. So there's a renderer called Ambient Mixer, which you could, for example, use with a talk-through a reproduction module feeding some headphones. And what this renderer does is basically just move or parsing an input signal to the sound card. So it's not actually a rendering process. It's not considering the source and receiver whatsoever. It's just routing the signals right through. But this might be very interesting if you combine it with another renderer. So remember, you can run multiple renderers in parallel. For example, if you want to have some background noise. And this is a very efficient way to get this, because if you would render all the background noise, this might be too much processing, and your computer might be limited. Or the processing power of your computer might be limited. Okay. So I already showed in the beginning the example of the room acoustics. There's a renderer for that, which is quite new, called Room Acoustics. Currently, it's bound to a binaural processing, and this works with Raven, our room acoustic simulation software. So we consider an actual room geometry and absorption, scattering coefficients for the walls, and so binaural room impulse is generated and convolved with the input signal is convolved with this PRIR, and we can use this, for example, with the talk-through or CTC, for example, to use it in our cave system, or the cave system next door. However, so to our external, I don't know if there's anyone externally in Zoom. This is unfortunately not public, since Raven is not publicly available. So the Raven is just for scientific and teaching purposes. So it's not in the general VA version. Another example are aircraft flyovers. So we all already saw this picture down here. There's this air traffic noise renderer, and this considers an inhomogeneous medium. So it uses the atmospheric ray tracing simulation framework to simulate curved sound parts, as shown here, and it considers the direct and ground reflection. So a direct sound and a ground reflection, and yeah, we can obviously use this to simulate or to auralize aircraft flyovers. And for example, we could configure this to be or to have a binaural rendering, and then use the headphones reproduction module with headphones, or we could do a VBAP spatialization and use the talk-through reproduction module and feed it into our loudspeaker system. However, since those simulations are very computational costly, this is not real-time capable currently. So the approach here is to do an offline rendering, and instead of directly writing the samples to the sound card, we can write them into a WAV file and then listen to it later on, or use it for listening experiments later on. This is actually you can do this with every rendering system or every setup that you do with VA. We can always do an offline rendering. So even though this renderer is called air traffic noise, you can still apply it to other scenarios. For example, a car pass by, because it also allows to use a homogeneous medium. So meaning we have straight sound paths. And then if we take a look at this scene down here, it might be reasonable to have a scenario like this. We have a ground reflection, and the car is mainly, or the dominant sound paths in this case might be the direct sound and the ground reflection, and then it might be used or a suitable approach to use this renderer for a car pass by also. Even though it's called air traffic noise, you might use it here as well. However, in scenarios where we have more structures around the source, this might be not sufficient, and then we need to, or might want to consider additional reflections at buildings, for example, but also diffraction. And for this case, we have the binaural outdoor noise renderer, and this is based on the image edge model implemented by, developed by Jonas Steen. So it allows to simulate sound paths considering higher order diffraction and reflection. And you see here also, I already put this wave file symbol here. This is of course also very computational complex, and it only works offline. Also, this renderer is still under development, so it's kind of in a beta version. So yeah, we are still working on making this more clean and easier to use. Yeah. Talking about real time, so my final example is sometimes if we have scenarios like those auto scenarios, we typically have sound sources or movement of sound sources that we already know. Like this aircraft, it has a fixed trajectory, and in this case even the receiver might be static, it just sits on this bench, but maybe you want to move your head while sitting on that bench. So the only real-time constraint that we have is actually the receiver orientation. And in this case, what you can do is you can render an ambisonic signal, store it into a wave file, so do an offline rendering for this part. And then you use this wave file as an input signal for the ambient mixer. And you can then, for example, connect this ambient mixer to an HOA decoding and yeah, use or feed this to a loudspeaker array. Or there's a binaural ambisonics mixdown, which allows to render binaural signals based on this ambisonics input signal. And this can be done in real time again. So this might be a workaround if you want to have a very complex scene where you cannot render all aspects in real time, but maybe you just want to have real time receiver orientation. Okay, that was my final example. So what's planned for the future? So regarding the new rendering concept, as you notice, there are currently only 2 new renderers, free field and air traffic noise. And what we're currently planning is to extend this to the outdoor noise renderer. So this, the idea is to get rid of or replace the old binaural outdoor noise renderer and allow to have outdoor scenarios also be rendered with ambisonics and bebop signals. And then I already showed you a lot of use cases. However, currently there are not so many examples which you can easily run on your computer to know how to configure and control VA to actually apply it to such use cases. So that's also planned so we want to create some MATLAB examples that are easily run on a computer, which are very simplified and might be a good starting point if you want to do a little bit more complex things or more complex things besides just have a free field rendering. And finally, but I want to put a very big question mark on that, maybe at some point we might also rework the reproduction modules. So similar to what happened to the rendering modules, there might be some rework there, but yeah, like I said, for now, a big question mark regarding this. Yeah, this brings me to the end of my talk. So I hope I could raise your interest in using VA. And if you want to check out the software, visit our homepage, virtualacoustics.org. And if you want to see a few examples of what you can apply to, we have a YouTube channel where you have a lot of videos that you can watch. Yeah, thanks.